Yeah, so we can use a little bit about vectors and a little bit of calculus, and can answer kind of a basic physics problem, projectiles, projectile motion here. We can figure out some components. Not going to get too heavy, but here's what we're talking about. All right, so let's say we got a projectile fired or shot or thrown. With angle of elevation alpha and initial velocity v0. So the question is, well, first of all, can we figure out the position function of such a thing? And then we'll maybe even narrow it down a little more. So what is the position function for our projectile? And again, we're going to use this. We're going to do this in vector, the context of the vector function. So can we figure out R of t here? Well, let's draw a little diagram. So all we know is we've got a projectile fired off at an angle of elevation alpha. So yeah, this initial velocity here, what that gives me is, if we think about this as a vector, this initial velocity gives me the magnitude of that vector that I'm firing off of me. So I've got to have some type of force behind this. So we're going to think of it as a vector. So this is angle alpha. Like I said, this v0 is just the magnitude of that vector. That we're talking about. All right. So what happens, yeah, is this. So we're firing it off there, but it's definitely coming back down because of gravity. So we're going to think about initially just starting off at a height of 0. Maybe make an adjustment to that, but yeah. So can we get a function that describes that path? Well, yes, we can. If so, here we're going to say there's no other force acting on this besides gravity, which is drawing it down straight down. But air resistance, we're not going to worry. Just cutting right through the air without any problem. Because that would factor in a little more. That's in a future engineering class. Okay. Yeah. So here's the way we can. Here's why it's brought up here, because, like we said, the only force that's acting on this projectile as it goes along is gravity. So that's the acceleration on this thing. So the acceleration is it's just gravity, which they found out that value, acceleration of gravity. We usually just represent it with g. Now, it too can be thought of as a vector, because what it's doing is the gravity is just acting here on this straight down, right, towards the ground. And so that vector, just think of it as this, right? It's negative gj, because it's down, so that that's the y component, if you will, right? So negative gj would be the acceleration vector here. So this is like a problem we just talked about. We've got the acceleration here, and so we can build our way up to the position here. All right, so where do we go? Where do we go from there? Well, the velocity then vector we could get here by doing the integral of a. So that would be the integral of negative gj dt. So that's a fairly simple integral. So the velocity vector is just be negative, g is just a number. We use 9.8 meters per second squared for it. I think they usually have us do it in meters. But anyway, it's just a number, and so negative gtj plus some constant vector. Yeah. So that's just a number, and so the antiderivative is just gt times j plus c. All right, now, so let's think about the c. As before, c is the velocity at v0, at time 0. And so at time 0, we're given that. Let's just call it the velocity vector at 0. So our v of t is just negative gtj plus v0, that v0 vector. Whatever it is, I mean, it's not specified, but it'll all come out with. It'll all work out here, okay. Now, our goal is to get to r of t, the position function. So wouldn't r of t be, just like before, wouldn't we integrate the velocity vector to get r of t, position vector? Yeah, so we're just working our way back. We've got the acceleration, do the integral, we got the velocity, do the integral of that, we've got the position. So r of t is the derivative here. Okay, so negative 1/2 gt squared, the j, or this part of it, and then we'll talk about this, but basically what we need to do is so the velocity vector function, it'll just have an x and a y component. It'll just be numbers. We can figure out, if we're given the initial velocity and we're given this angle alpha, we can figure out what the ij, but it's just going to be a number. And so as far as I and j go, so it's just, you got a number, so you multiply by t. Anyway, we'll get more specific about it here in just a second. But we also need to add in this constant function. Well, again, r of 0 is going to be that d constant vector function, or vector part. So what does that mean? That's the position at time 0. What's the position at time 0 here? Well, by our assumptions, it's 0, right? 0, 0. So, yeah, d in this case just winds up being 0. So r of t is just negative 1/2 g t squared j plus v0 vector times t. Okay, now let's work on that a little bit. So that v0 vector is that vector we've got right there. So I just need to come up with a better form of that v0 vector. Well, just kind of look at it here. Do kind of a little right triangle on it here. The I component of the vector here, let's call it x0. And then the y component of the vector we'll call y0. And we know this is v0, just the initial velocity that we're given. We know because that's, like I said, that's the magnitude of that, how long that vector is. Anyway, so it's x0 I plus y0 j, but that still doesn't really help us. If I get it, though, in terms of what's given, how could I write x0 in terms of the v0 and alpha? Well, cosine of alpha would be x0 v0. And so isn't x0 v0 cosine of alpha? And then the same thing, I could do the same thing, but sine of alpha is y0 over v0, right? A little bit of trick. So y0 would be v0 sine alpha j. Just from that right triangle relationship. And, or, yeah. So, factoring that in here, what do we got? So R of t is negative 1/2 gt squared j plus v0 cosine alpha I plus v0 sine alpha j t. Here's what we got. R of t, the I part is going to be v0 cosine alpha times t. The j component is going to be negative 1/2. Let's write it this way. Let's write it this way. v0 sine of alpha minus 1/2 gt squared. That's going to be the j component. There you go. So the position, no matter what your angle is, what your initial velocity is, this gives you the position of that projectile. Now, to break it down a little more, here's what we're going to do. They call it the parametric. I guess I could. Put it over here. So R of t is v0 cosine alpha. T, the I component, and then v0 sine alpha minus 1/2 gt squared, the j component. And so another way they phrase this is, therefore, the parametric equations of trajectory are then x equals this v0 cosine alpha t times t. And then the y is v0 sine alpha minus 1/2 gt squared. So calculus gives us these particular equations. So let's do this. Oh, before I do the problem. Now, one slight variation, I guess you might say. All right, so this is the initial height is 0. Okay. So it's firing the projectile just from ground level. What if I fire it at a height that's not 0? So what if the initial height is not 0? I guess call it H0 or something. I erased everything, didn't I? I was going to go back and... Well, okay, we just do it from here. Well, the initial height is at time 0, right? So all that's changing, if we go back to our little diagram here, all that's changed, instead of height to 0, I start here at a different height. So what is that going to mean? Well, all it means is that my x value initially is still 0. So I'm starting here at t equals 0. The x value is still 0, which that's what you would have here. But I want the y value to be this h0, right? So how would I get, instead of x is 0, y is 0, I get x is 0, y is h0. Well, I don't have to change the x value at all. The y value, all I have to do is add in the height there. And everything else stays the same. So, yeah, if you start at initial height of h0, just add it in to the y component, the j part if you're on your vector function there. All right. So let's say we've got a projectile is fired. With initial velocity (150 meters per second), and the angle of at an angle of elevation of 45 degrees. From a position 10 meters above the ground. Okay. So the question is, where does, well, let's do this. All right, what are parametric equations of trajectory here, first of all. Okay, so that would be x equals b0 cosine alpha times t. Y equals b0 sine alpha t minus 1/2 tt squared. I think I forgot the t here. Okay, plus h0, since I'm starting at a different height than ground level. So that means x equals, all right, so what is v0? V0 is just the initial velocity, so that's 150. Cosine alpha is just the unit of elevation, is 45. There's t, so that's going to work out to be 150 times square root of 2 over 2 times t, so that's x is 75 times the square root of 2t. That would be the x, specific x one. All right, then the y is v0, 150. Sine of alpha, alpha again is 45, so that would be square root of 2 over 2 again, t. Minus 1/2 g t squared plus h0 is the height, so plus 10. All right, so let's, again, like I said, G, we'll just approximate it with the 9.8 meters per second squared. And so that'll make our Y 75 square root of 2t minus half of 9.8, so that'd be minus 4.9 t squared plus t. So those are my trajectory equations. Questions or concern about that? Here's B part then. Where does the projectile hit the ground? And with what speed? So, several parts to that. Where does the projectile hit the ground and with what speed? Now, the first part of that, let's again think about our little problem here. Yeah, we've got this projectile, it's 10 meters up, so we've got it firing off, hitting the ground out here somewhere. So, first of all, what is that? What value am I looking for? Well, I want to know where. So, basically, what I'm trying to figure out is the x value, right? How far out there it is. So the x value is what? And the other part to this, important part to this, is what about the y value? Well, The y value, we definitely know, yeah, it's 0, okay? So we're looking for the x value when y is 0. That's what we're looking for. For the projectile hit the ground. What's the x value when the y is 0? Well, if the y is 0, here's what I've got. Y is 75 square root of 2t minus 4.9 t squared plus 10. And I want that equals 0. Well, it's just a little bit of a quadratic formula problem there. Negative b plus or minus square root b squared minus 4ac all over 2a. I guess I don't have it in the proper order there, but yeah, just figure that out. The b is the 75 square root of 2. So do that squared here. And then minus 4 times a, the a would be negative 4.9. C is 10. 2 times a, so it'll be 2 times the negative 4.9. And that'll give us our solution there, give us the t value, because isn't t is what I need to figure out my x value. I need the t value there. So solve that, and that'll give us that. I get that to be approximately 21.74 seconds. Check me on that, but that's what I got. So the x value then would be 75 square root of 2 times the t, which is we now found out to be 21.74. And that gives me approximately 2,306 meters. So that thing, so this allows us to figure that distance out, how far out it's going to go. Now, what about the speed? What about the speed? Well, remember speed, that's just our magnitude of velocity. So there's a little bit, I've got to figure out what is the velocity here. Well, the velocity is the derivative of the r function. And remember these are going to give me the components of the r vector function. So 75 square root of 2 t, that would be the I, and then that's the j component. So basically I'm just doing the derivative of these two things to get the velocity. So v of t would be the derivative of that. So it'd just be, derivative of that would just be 75 square root of 2 I plus 75 square root of 2 minus 9.8 t. Get the j component, derivative tends to 0. So that's our velocity function. The speed is the magnitude of that, so our speed is going to be square root of that squared plus that squared. And I know, again, I'm trying to find the speed when it hits the ground, so I know the time it hits the ground is this 21.74, so the 75 square root of 2 minus 9.8 times that 21.74. take that square. So it's just a little bit of calculating there. I get 151 meters per second. Approximately there.